it's my pleasure to introduce today's speaker, Professor Alex K.Y. Jen from the University of Washington at Seattle. Pardon me, I was running. Alex received his PhD in chemistry just down the road from us at University of Pennsylvania in 1984. And he actually stayed around this area for quite a bit. He started working with Allied Signal, and he was with Allied Signal for 8 years before joining Anychem America as the group leader there. And then he became the vice president of the Optical Materials Division of ROI Technology in 1995. After which he decided to embark in the academics, so he was with Northeastern University before finally settling at University of Washington in Seattle in 1999. Alex is currently the Boeing Johnson Chair Professor of Material Science and Engineering, and he's also a professor in chemistry. He's actually the department chair of the Material Science Department. In addition to that, he's actually successfully led several federally funded centers, including most recently a DOE-funded program in Solar America Initiative. In addition to being chair, he's the founding director of the Institute of Advanced Materials and Technology, and he's won many awards. He's a fellow in numerous societies, including the International Society of Optical Engineering, the American Association for the Advancement of Science, the Optical Society of America, and this morning he told me he's been inducted a fellow of PIMSI of the American Chemical Society. He holds the Changjiang Endowed Chair Professorship from China's Ministry of Education. He's also the recipient of the Faculty Research Innovator Award from University of Washington and is a member of the advisory board of the Institute of Chemistry of the Academia Sinica in Taiwan. Alex's research interests are wide range, but he's been focusing on the materials chemistry for photonics, optoelectronics, and biosensing. And now he will share with us his views on how organic electronics and photonics can contribute towards solving today's energy challenges. So, Alex.
Great. Thank you. Thank you very much, Elaine, for your very nice introduction. First, I would like to thank the committee for inviting me to come here to share my personal view of the Erdinger Center for Energy and the Environment. Today, I would like to utilize, to try to share with you, our recent approaches of utilizing molecular design, self-assembly, and also interface engineering to significantly improve the performance for polymer electronics and photonics. And I would like to utilize 3 different examples. One is successful design for polymer-based solar cells. And then another one is work we did in the NSF-funded Science and Technology Center to develop ultra-large electro-optical activity materials, enabling the device development to form ultra-low voltage information processing. And at the end, I would like to briefly show you, some of the technology I think Princeton people are very familiar with. This actually Professor Stephen Forrest was a pioneer for OLEDs, but then takes instead of layer by layer deposition of the molecular-based OLEDs, then we utilize solution process polymer light-emitting diode and try to make the white light LED. Utilize that for solid-state lighting. And also to show you potential impact generated potentially if we can deploy this kind of device, so dramatically impacts our environment. So first, I think after last year's roller coaster ride of oil price fluctuation, I think that everybody now convinced that one of the most important technology challenges we are facing currently is to meet the energy demands of this growing world population in an environmentally and also geopolitically sustainable fashion. And with continuing advancement of the technology, and people can find, more coal and also oil, okay, and can continue to sustain maybe the burning of the fossil fuel for 100 years. However, by burning the fossil fuel, you cause global warming and air pollution, okay. So this is one of the very challenging problem we are facing today, okay. Need to develop a coherent solution, okay, to provide, clean energy and also to impact our environment. So today, the first part I would like to talk about is based on our recent development, utilize molecular design and also interface engineering to really improve solar cell performance. Okay. If you look at the work consumption, energy consumption, okay, and is mostly divided into three of the large components by burning the fossil fuels, okay, and renewable energy only accounted for about less than 1% of the energy being used. Okay. However, if you take a deeper look at that renewable energy, and then most part of that is being used by deployed by using wind as a source for energy, and part of it for biomass. The solar cell type of renewable energy only account for less than 6%. Okay, and however, already accumulated for around $13 billion of a market. If you look at the abundant resources in our environment, okay, compared to all the different energy sources, okay, and solar energy is one of the energy source potentially can surpass all of the combination of other energy sources. 1 day of the sunlight equal to the whole consumption of the energy consumption of the whole world, right? So, but then if you look at this have a tremendous potential for us to really explore the full potential of the solar energy. However, if you look at that, why not everybody have the solar cell on top of their roof, okay? And if you look at that, by burning the fossil fuel, it costs less than $1 per watt of burning the fossil fuel. But the current technology utilized based on the silicon, okay, is more than $4, $5, okay, per watt, okay. So this is a dramatic difference in cost, okay, dramatic hinder the deployment of the solar cells. Okay, if you look at a lot of European countries utilize solar cells, they are heavily subsidized by the government. Okay, so if we really want to have a sustainable, deployable technology, you really need to develop your photovoltaic cell below $1 per watt. Okay, so people did very brief calculation talking about how much of the solar cell coverage do we need in order to really generate enough energy for the United States. This shows you, okay, if we can have a Polymer solar cells and with a 10% efficiency and cover Arizona with about 150 miles square of areas, okay, you can generate enough of the electricity to power whole United States, okay. And if you look at that, certainly, in order to cover 150 miles square of the areas, okay, not going to be achieved by just fabricate batch by batch of a silicon-based wafers, okay. So one of the possible possible technology is based on polymer, large area printing or large area roll-to-roll process polymer solar cells, okay. And another analogy we can say, right? If you look at polymers have been widely deployed. We have produced a ceramic film, okay, potentially can wrap around the whole United States several times, okay, and then the process already exists there, allow us to deploy for a roll-to-roll printing process, okay. So if you look at a polymer-based solar cell, I would like to bring in the argument because of the lightweight and also and also solution processable, you can process in all the different kind of form. They can have fine application from niche market for consumer products, okay, use as chargers, okay, for trickle chargers, okay, for all the appliance, okay, portable electronics. And you can also potentially utilize that for large area of grid power, since 1/3 of population in this world, about 2 billion people, okay, cannot get access to the grid power. Okay, so this potentially can also generate some convenience for those people. But one of the great advantages for solar cell, instead of everybody have a common concept, solar cell should be put on top of the roof, okay, or on the side of your building, right? And basically, because of material of the organic conjugate polymer, you can engineer that. So this material you can engineer to provide you some semi-transparent material, okay? And as a result, you can laminate between the two windows, two pieces of window, okay, perfectly to avoid all the outside harsh environment, like the sunlight, like wind, sand, and snow, all the different kind of environmental aberration, okay? So by putting that, okay, if you can envision for big city, all the office building, high-rise, you have all the tint color windows, okay? Those are all the potential place for fine application for semi-transparent solar cell. So when we start to talk about solar cell, we need to understand what's the fundamental mechanism behind this in order to make the solar cell work, right? So this is a very brief illustration. Okay, when you talk about typical donor or acceptor composed polymer solar cell for p-n junction in here, when you absorb light, you generate exciton. Okay, and the exciton, because they have only lifetime, say about nanoseconds, so can only diffuse about 10 to 20 nanometer of the diffusion length. Okay, so before the exciton decay down to ground state, you need to find the interface for them to dissociate this as into the separate charges. Okay, hole in the electrons. Okay, so then whole electron, because of built-in potential of a different electron. Okay, then you can transport through the material medium and to be collected from the photogenerate current. Okay. But if you look at the current configuration, in order for this exciton to be separated from the different charge carriers, this guy need to diffuse quite a long length. Okay, before it can reach the interface, usually this either fell down to a ground state. Okay, so then you waste your photons. Okay, so another way to solve this problem is to create so-called bulk heterojunction. Okay, instead of you just have a two-layer, have a junction here, then you create through the phase separation. When you anneal two different incompatible materials, then you create the this phase separation. Okay, so you form multiple junction. Okay, so you have much short distance. Okay, for exciton to find the interface to dissociate and find their corresponding conducting paths, okay, be collected. Okay, so in order to really develop devices, okay, suitable for commercial or large-scale deployment, the current challenges for OPVs is how do you to improve your efficiency above 10%. Okay, currently the highest OPV is around 6% right now, compared to amorphous silicon, compared to all the other CIGS type of solar cells, still lower than those competitors. So, and also, how do you develop the processing methods, okay, to lower the cost, and also how do you improve their stability? Because one of the common challenge in organic material is environmental stability. Okay, so in order to really achieve that, we need to have coherent and also integrated approaches. Okay, one is, for example, you have to go through the material engineering, allow you to have tailored absorption can cover the solar spectrum, sun spectrum, and also the charge transport allow you to be collected, okay, in at the opposite electrodes. Okay. Then also you need to have interface engineering, allow you to have a better charge selection, charge also collection at the interface. with new device engineering, you can potentially create a new device architecture, allow you to print or try to process your device in a much simpler way, and also create much more stable device. And then at the end, okay, how do you utilize the process condition, okay, to create desirable morphology, okay, and also allow you to utilize all the different kind of printing process, okay, like evaporation or the inkjet printing to really create your solar cell. So within the DOE-funded Solar America initiative, we sort of adapt integrated approaches, try to solve the problem, just like I described before. Okay, so we basically can develop a material can actually, with a tailored absorption, almost cover the whole sun spectrum. Okay, and depending on your design, your molecular structure, the material can be semi-transparent, but still with a relatively high mobility and also with a high solar cell efficiency. And also we utilize a self-assembled monolayer, for example, like C60 containing SAM, okay, and utilize this to serve as very good interface to collect your electrons. Okay, so as a result, you can improve your selection of your charges. And with different printing or coating process, you can basically take a very stable metal and then do a printing process to generate your corresponding cathode or anodes. And at last, in order to really improve the efficiency of your solar cells, we can basically take the material with the complementary of their absorption. Then you stack them up, okay, as a tandem solar cells. Okay, so you can minimize their footprint, but then you can increase their efficiency. So within the next maybe 15 minutes or so, I would like to sort of work through the slide step by step, okay, to explain this to you. We utilize SAM to provide several different functions. Okay, when you have a SAM to work on to coat down your, for example, substrate with a metal oxide electrode. Okay, then you can actually control the charge coupling as the interface, and also depends on the shape and also the energy of the material molecule you sort of covalent bond on the substrate. You can use that to nucleate the growth of the top layer, so you can actually get a much better control the morphology with a much better conducting path. Okay, and also you can utilize the SAM to passivate a lot of those hydroxy selenol containing or those are acidic hydroxy group containing surface traps. Okay, all those traps are potentially decrease the efficiency of your devices. And the last one is to utilize molecular dipole. Okay, depends on the dipole's point position. Okay, then you can selectively either increase your work function. Okay, for example, in this case, for facilitate charge injection, and also or you can lower the work function. Okay, under your LUMO. Okay. So I would like to utilize a couple cases to show you. First one is based on so-called conventional device structures for polymer-based solar cells. You basically utilize ITO side and as an anode, and you on top of that you have low work function metal as a cathode. Okay, so you basically have this is a blend system with a donor and acceptor, like C60 blend together to create bulk heterojunction. Okay, when you shine light on it, then electron will be collected, goes to this low work function electrode, and whole goes to this conducting polymer as an anode here. You can get the efficiency around 5%, but however, because the low work function you use for cathode, okay, and you actually create a lot of problem for environmental stability of your devices. Okay, so people, in order to really improve some of the optical buffer, utilize to maximize the optical field. Okay, and also to provide some buffer layer on top of that, people utilize titanium oxide or zinc oxide to coat on top of this blend. Okay, and then people have certain degree of success. However, with the titanium oxide, you have mobility, or the electron mobility around 10 to the minus 4 to 10 to the minus 7. Okay, so in our case, we try to substitute that instead of titanium oxide, and we use zinc oxide, which have about 4 orders higher of the mobility for electrons. And then on top of zinc oxide, we can grow a layer of the SEM to help to collect the electrons. Okay, so this is one based on the conventional approaches. And another approach is, how about we take the conventional device structure, invert that, put the most sensitive part, the cathode part, bury underneath here, okay, and then utilize the substrate to protect your most sensitive part, okay. So based on this, we have another area SEM, okay, in here to collect electron here. Then in here, you can actually use that to collect holes. So in this study, I'm going to show you. First one is based on the conventional device structures. Okay, utilize ITO as anode and also metal here as a cathode. Basically, on this polymer blends, we have a spin coated one layer of zinc oxide nanoparticle, and try to grow on top of this zinc oxide with some SEM. And this SEM have 2 different categories of SEM. One is based on carboxylic acid with a different kind of either electron donating group or electron withdrawing group. Okay, with that, you can have different kind of dipole moment, range from minus 3.9 dBi to 3.7. Next kind is the based on aliphatic-based SEM, okay, and we also introduce some linkage. Potentially can have a functionality here to coordinate with the metal electrode you try to evaporate on top of that. So one is based on the conjugated system. Another one is totally based on aliphatic system. We will try to see how we're going to do that. So how are we going to choose proper SEM in enhancing the interfacial property and also adjust the work function between your material and also your corresponding electrode? Okay, so basically for both heterojunction device, the open circuit voltage of the device is based on the LUMO of this lowest unoccupied molecular orbital energy of your acceptor. This is C60, and the HOMO, that's the highest occupied molecular orbital of your donor. Okay, so difference in that is give you the more or less define the open circuit voltage. Okay, however, if you evaporate different metal depending on the metal work function. Okay, if you have some of the energy barrier in here, so your effective open circuit voltage instead of as interface here, it become much smaller. Okay, so one. When we slap a layer of zinc oxide, try to help to collect the electron, okay, because LUMO energy level actually match reasonably well, so you have ohmic contact at this level here. However, you still have some energy barrier here, so your open circuit voltage is still limited, quite limited. When we start to put SEM on top of zinc oxide, depends on the direction of this dipolar SEM, okay, then either you can increase the work function of your metal or reduce the work function of your metals to match your energy level of your zinc oxide here. Okay, as a result, you can have much larger open circuit voltage of your devices. So if you look at here, this slide to further explain that. Okay, when you have a SEM form on zinc oxide, when you have carboxylate here, you form a small dipole point toward zinc oxide direction. Okay. However, this molecule, since they have their intrinsic dipole point this direction, so it's a larger. So net dipole is actually point toward the free space. Okay. Vice versa for electron withdrawing substitute molecule, then you have net dipole point to this direction. However, when you start to slap a layer of the metal, okay, since you have a cathode, you slap on top of this SEM, right? And as the metal and the molecule interface, when you slap a metal on top of that, you have a highly polarized interface. As a result, you generate another induced dipole here. This is a very, very large dipole in here, okay? So instead of originally, you have dipole point this direction, but then with this large dipole, then now the net dipole actually point toward zinc oxide direction right now, okay? So this slide to show you, okay, when we indeed put this SEM on top of the zinc oxide, okay, you can see that they have a dramatic influence on their device efficiency, okay. You can see that with most electron donating group in here, okay, so you can have very nice field factors and very high device efficiency, okay, and also a relatively high open circuit voltage. But if you start to move to different direction of a dipole, okay, actually you can see that you have a very small open circuit voltage because that energy barrier is further significantly increased, okay, and also your device performance is also very poor, okay. So this, if you look at that, this is the one without the dipole, okay. So because aluminum, you have work function is about 4.2 electron volt, okay, which is very close to zinc oxide. So you don't really get that much net benefit, okay. However, when you take higher work function metal, like a silver and gold right now, right? Originally, if you look at that, if I don't have this SEM, you have a very poor performance, okay, in here. This is a dotted line here, okay. But when you start to introduce this layer of SEM, you have significantly improved the device performance, okay, on this. But when we observed this, we were quite excited. But but then we actually are stunned by the discovery of instead of the conjugate SEM, then you have aliphatic SEM, okay, actually provide you even better results, okay. If you look at the SEM in here, because especially there's a double end SEM. One end you can link with zinc oxide. On another end, you can form the bonding with gold or silver as this interface. Okay, as a result, okay, you can actually have a greatly reduce the series resistance, and also you terminate a lot of interface trap. Okay, as a result, you can have very high shunt resistance, parallel resistance. Okay, and you can see that the device performance, okay, are significantly improved because of that. Okay. With that said, those were based on the conventional device structures. Okay, and how about we said, okay, take this thing, you flip around. Okay, take the zinc oxide coated on the cathode side, and you use this side to actually build an inverse structure to collect electrons. Okay, and with this structure, we can, because the room temperature process, we can actually make the flexible solar cell device very easily and utilize conducting polymer to collect hole on top. Okay, because when you evaporate, for example, silver on top of that, during the evaporation at the interface, you have some very thin layer of silver oxide formation. That is from the energy level, the work function is exactly match of the P dot. Okay, as a result, you have very efficient hole collection. But one of the very surprising results we discovered from this, when you coat this, make this device based on the polymer substrate without any encapsulation, right? And if I try to make this device with a conventional device structures, in 4 days, okay, exposed to outside environment, okay, then this device would completely die. Okay. However, if you have this device utilize invert polymer structure, okay, even after 40 days, you still have more than about 85% of your device performance still remain. So by changing the sequence of your device configuration, okay, and you can greatly improve your device performance and also stability of the device. So we took one step further. Instead of just have a zinc oxide, we actually take this ITO, coat one layer of the self-assemble one monolayer of the C60. Utilize this C60 to help nucleate on top of the PCBM formation. Okay, you can nucleate that, so you can have much better conduction of C60, okay, so you can transport electrons, and electron can be collected through the C60 here, goes through zinc oxide and into your cathode, okay. With that, you can see that with the inverse structure, you can build almost a 5% performance device, and you can greatly simplify your device fabrication. You can build a relatively large area device relatively easily, okay. So this is one evidence to show that, okay, when you template with a C60 at the bottom, okay, people said, okay, how do you know you can nucleate the top layer formation of your C60? Okay, this is one evidence to show that when we fabricate our device in the FET type of configuration, right? Because when you have a full bias of that, okay, in here, biased positively, okay, and you can see gated positively. Then, because when you run the FET, okay, the interface of the dielectric usually the area for determining your charge transport of your charge mobility of your devices. If I have a C60 SEM, this is a red layer here, and if I can nucleate nicely of the C60 concentrate as an interface, then I will selectively have only the improved electron transporting property, which is actually proof in here. Okay, so you have C60 with SEM have much higher mobility compared to without the SEM. Okay, so this gives you some direct evidence. Okay. This does have some effect on that. Recently, we are utilizing, I'm collaborating with Dave Ginger, utilize near edge X-ray, try to prove, that you actually can prove that nucleation through the almost 100 nanometer range can create the difference on the surface. We already observed some preliminary result to prove that. Okay. So with that said, I utilize a couple of slides to summarize this part of my talk. Okay, to develop device through processing through SEM interface engineering, you can improve the performance. How about the new device material composition? Okay, can allow you to really harvest the whole sunlight spectrum and also improve your device efficiency. You can see this is a plugin containing polymer. It's a relatively transparent, okay, but then it has a relatively high mobility, 10 to the minus 2, okay, very high mobility for this kind of amorphous material compared to the polyester archoselfine, the crystalline material. Okay, you already have very high mobility, but still relatively transparent. So this kind of material will be ideal candidate for laminate between the window type application. And recently, try to engineer a material can sort of cover the whole sun spectrum. Okay, we are actively in developing so-called small bandgap conjugate material, okay, conjugate polymers. And the conventional approach in developing small conjugate polymer usually utilize so-called donor-acceptor substitute the conjugate polymer. Okay, and when you build this kind of material, although you can really, because of charge transfer property, you can shift your build a small bandgap material and shift your absorption to near IR range. Okay. However, because of the energy difference here, the acceptor part usually acts as a trap. Okay, for your material. So this kind of material, you have very low mobility. It's more or less you drive on the New Jersey Turnpike every 50 feet you have a pothole. Okay, so how can you drive it fast, right? So in order to develop a methodology to solve this problem, we actually try to separate this two section apart, right? One is you have a backbone. You can be responsible to really transporting the whole, okay, and then you can have, utilize technology we develop in nonlinear optical material. You can develop those dipolar die can selectively absorb different absorption ranges, okay? But then this critical thing is you develop this acceptor can have match energy level to your C60 or C70. You can see that by utilizing this approach, it offers great variation of different kind of molecular composition you can choose, okay? And our preliminary result already show very promising result. You can take this material and already have about 4.8% in your device performance. Okay, so this is very encouraging because just the initial try already match the best performance for state-of-the-art polyester archoselfine. Okay, so this is my last slide for solar cell talk. People talk about in order to really make affordable solar cell, okay, if you try to utilize silver, try to use a gold as your electrode, how can you build a solar cell with affordable price, right? So if you look at the versatility of this SEM treatment or the interface engineering, you can build your invert device. Okay, right now you can see all the different kind of metal we tried. We can take the copper, very cheap metal, okay, and then make it into a very efficient solar cell devices. Okay, so basically this solution process and also your device fabrication can be generally applicable to all kind of metal electrode. Okay, so with that, I would like to sort of shift gears. Okay, the first part of my talk is talking about how do you develop potential energy source, okay, with solar cells, right? So second part of my talk is actually try to give you two examples. One, is based on ultra low voltage computation or information processing, okay, and third part will be talking about solid state lighting. Because if you really want to solve energy problem, you need to have a coherent solution, right? Not only the energy source, how efficiently you utilize your application, okay, and potentially can dramatically save energy. That's also another option. So this is this part of the talk is talking about the very efficient electro-optical material we develop allow you to have very efficient information processing. So this is actually New York Times talking about, in the next 4 years or so, we will experience a tremendous traffic jam on the internet highways. Okay, the reason because of exponential growth of the demand for a video game or game industry or the video conferencing. Okay, and for example, you have a video site, YouTube, okay, can consume as much bandwidth as entire internet in 2000, okay, just that because of all the movie they send around, okay. So there's a dramatic need for us to really find a way to really provide a solution to solve this internet traffic, okay, traffic jam. So one possibility is to tap into nonlinear optics, okay, and so in order to have very efficient so-called electro-optic material, you starting from building blocks of a molecule, okay. And if you look at this, a typical so-called dipolar nonlinear optical molecule, you have a donor part, you have a conjugated bridges, and you have acceptor part. And because it's a very efficient conjugated bridges and donor and acceptor, you have relatively large charge transfer, okay. As a result, it creates relatively large dipole, okay. And if you look at that, when you start to put those molecule in the polymer substrate, right? And those dipoles tend to pack because antiparallelly to reach the minimum energy state. However, to introduce second-order nonlinear optical effect, you really want those molecules to align into this non-central symmetrical fashion. Okay, so this is one of the very challenging problems that have been existed for past 20 years. Okay, people spend billions of dollars, okay, investment try to solve this problem without much of a success. Okay, and this is a very challenging problem to really build a material with a relatively large electro-optical coefficient. Okay, in order to have this second-order nonlinear optical effect with large electro-optical coefficient, if you look at this equation here, and you need to simultaneously solve three different things. You need to increase the number density, means more of those active molecules in your matrix. And you need to develop your molecule with large beta, it means hyperpolarizability of your molecules. And then you need to find a way to orient the dipole efficiently to create this poly-induced polar order. Okay? However, when you start to increase the number density, then those dipoles start to see each other. Then they start to interact with each other, okay, with through the very strong intermolecular electrostatic interaction. Okay, so you will be really inhibit your alignment. Okay, so in order to solve that problem, we try to go through a couple of different innovative approaches to create some molecular self-assembly approach, try to improve the poly efficiency. So the first thing I would like to show you, okay, is when you look at the typical molecule, okay, I need to step back a little bit. This approach I've tried to introduce to you is based on taking advantage of the quadrupolar interaction to really improve the assembly and also improve the Polymer efficiency of your materials. If you look at the conjugate molecule, typically diphenylstubine, okay, because the pi electron delocalized along the conjugate backbone, you have electron sort of center along those center part of your molecule, okay? So the center part is the electronegative, the outside part electropositive, okay? And if you substitute this molecule with a fluorine atom, okay, because the high electron affinity of your fluor atom, okay, right, suck electron to the edge, okay, you can see they have a much higher electron density. So the center become electropositive. So if you try to crystallize either diphenylstubine or fluoro substitute stubine, okay, those type of molecules tend to crystallize into a center to edge type of herringbone type of structure like that, okay, because they try to avoid from those negative charge sit on top of each other. However, if you co-crystallize diphenylstubine and fluorostubine, then they form a perfect column type of a stacking, okay, allow you to have very nice self-assembly, okay. So if you consider one of this per ring of the benzene and the fluorobenzene, that kind of interaction is the interactive force about 3 to 6 kilocalories or more. If I can increase the number of those rings, okay, so those interactive forces you can tap in is not trivial, okay. So basically, we did a model study by taking a nonlinear optical chromophore, try to build the diphenyl fluorobenzene substitute to type of dendrons, and another one is diphenylendron, okay. And when we try to make the model compound, indeed, they co-crystallize into alternative type of manner with spacing, interplanar spacing of benzene and fluorobenzene about 3.7 angstrom, okay. And so this shows you they can indeed form a relatively tight pack, okay. So, if we try to well, the movie somehow cannot work in here. So basically, you take the dipolar molecule, then you functionalize this dendron. Those dendrons serve a couple of different purposes. One is to sort of separate those dipole apart. Another one is during the your heating and pulling process. Okay, when you heat it up, this molecular glass, okay, can sort of be dissociated. But then when you apply electric field, okay, then all the dipole will be aligned toward similar direction. But when you cool down, all those self-assembling forces will start to kick in, okay. As a result, you can form a relatively stable lattice, okay. And this is the result to briefly show you, okay. And when we have just a single dendrons, okay, you don't really see your electro-optical activity have a significant enhancement, okay? But when you start to show this as a symmetrical HDFD type of arrangement, you immediately have an effect of a 2 and 2.5 enhancement of your electro-optical activity. But most importantly, if you look at that, the material have relatively low TG, okay? But then when you heat it up, after you pole align them, right? And you heat up long-term heating at 50 degrees C for 30 days, this material still about 92% remain their original alignment. Okay, means this interactive forces really kick in to maintain the lattice polar order. Okay, so from the reviewing the this equation, you can see that in order to really increase R33 number, you simultaneously increase number density, beta, and also cosine cubic theta. We can achieve the Poly-induced efficiency by utilizing self-assembling approaches. However, when we start to take another much more active molecule, like blue, indicated by this blue arrow, right? Arrow, and you can dope into this lattice. When I organize that, this blue arrow will be organized along this order lattice. Okay. As a result, you can see that this give you R33 as high as 327 picomillivolt. I need to give you something to calibrate with. The best inorganic material based on lithium niobate, give you electro-optic coefficient around 31 picometer-volt. Okay, so this is represent about 1 order higher development. This is more or less, like say, you have a silicon, you have 1 order higher mobility than the current single crystal silicon. Okay, so this is can be explained by this slide. Okay, when you consider the reason why this high efficiency can be achieved is when you create this order lattice. Okay, when you further dope with your second chromophore, if you consider just a gas particle model and this without this lattice, right, then this chromophore can access 3D direction. Okay, so then the polar order is the dipole time the electric field divided by the thermal energy. Okay, however, if you organize them in the order lattice, okay, then you put another arrow come in, right? And this molecule can only, instead of rotate 360, then can only up or go down. Okay, as a result, you can take that a factor 5 away. Okay, so you can improve your device for about a factor 5. So this is a dramatic improvement for your electro-optic coefficient. We can further molecular engineer this environment. Okay, when you tailor their environment around, for example, this molecular dendrons molecule, you can see they have a much narrower absorption because instead of take this chromophore dope into the polymer and you can form the aggregate, form inhomogeneous broadening of your absorption. Okay, then this thing can actually have a much narrower absorption. And just this one molecule by itself is already almost 9 times of that lithium niobate. Okay, so this is the chart to show you through one of the integrated effort within NSF fund STC at the University of Washington. In the past few years, okay, we have developed electro-optical material now reach electro-optic coefficient around 600 picometer-volt. So this represents about 20 times that of your best lithium niobate device performance. And with that development, when you work with very clever device engineers, right, they can really take advantage of this ultra-high electro-optic coefficient and develop into a device with ultra-low voltage, okay, to modulate that. Okay, so with that said, maybe I skip this this slide to talking about another unique thing about such a high electro-optic coefficient and also very stable electro-optical material. We have been working with Intel, okay, try to solve one of the very challenging problem because Intel, they can continue to improve their performance microprocessor, but they still have a tremendous problem to communicate with their peripheral chips, okay. So in order to do that, so they will try to develop some solution to combine photonics and also electronic together. So you use your CMOS CPU at the bottom, and on top of that, you based on the photonics material, okay, and you can utilize fiber to go through the different kind of ring resonator to modulate your information to go through that for interconnect, okay. So this is another very exciting development based on the so-called silicon photonics. Silicon have been widely used as an electronic material, but never been really utilized for photonic material. Okay, but then if you look at that photonics, usually the device size around a centimeter size. Electronics always micron size. They have a severe mismatch of the size, right? But with recently the development of nanotechnology, utilize e-beam lithography, we can create nanoslot waveguides. Okay, can create this thing. Then you can, because of this continuity of their dielectrics, okay, so then the field, okay, T mode of the silicon guiding mode can concentrate in this nano gap. When you put the nonlinear optical material inside, okay, you can significantly improve their polarization, okay. So this allows you to get a device with a very low voltage, okay. So this show you one slide we borrowed from Luterra, okay, a silicon photonics company, talking about, they quote one of the comments from Intel, so communication VP. in 10 years, optics will come on every desktop chipset. Okay, means you can take the photonics now to sort of combine with the electronics. When you start to shrink the size of your communication distance from metro long haul to all the way to board-to-board, chip-to-chip to intra-chips, right? The number of the device, okay, increase dramatically to billions. Okay, so this things can dramatically improve the energy consumption of your information technology. If you look at that, okay, because recently, in order to come prepare for my visit here, I have been Googling a lot, okay, on the internet, right? Then I just learned from Harvard, okay, some researcher did some investigation, said, every time you Google, okay, and you cause carbon dioxide emission of 7.5 grams, okay, and then if you really think about that, how many billion times people Google on the internet, right? Then you create dramatically the amount of carbon dioxide emission, okay? The reason why, because they build thousands of the sets of a little cluster computer together, okay, and take a tremendous energy to run this kind of computer and generate tremendous heat out of this kind of setup, okay? So by creating ultra-low voltage switching device in the computation, you can also significantly reduce the energy consumption, okay? So this is a non-trivial. So the last 5 minutes or so, I would like to utilize some of the work, okay, actually quite familiar to Princeton audience here, is based on OLED or polymer light-emitting diodes, right? And this is talking about another application potentially can significantly lower the energy consumption, okay, which can also dramatically impact the environment, okay. So if you look at the incandescent light bulb and also fluorescent light tube and also LED-based solid-state lighting, okay, you can see dramatic difference in their efficiency, okay. So if you, for example, use incandescent light bulb, okay, you have 5% efficiency. You spend all your effort trying to harvest sunlight to generate energy, then you waste 95% of that and generate heat, okay? So you need to use the air conditioner to cool it down, so you double waste of your energy, okay? So if you look at that, okay, the basic mechanism to make the LED, okay, is based on just a reverse concept of the solar cell, right? So instead of you shine a light to generate exciton, then you find a way to separate the charge to different charge carriers, then collect them efficiently. Now, you have to sort of inject your hole and electron from anode and cathode and try to find a way to let them recombine very efficiently and then confine the exciton, okay, to improve the efficiency of your exciton generation, okay. So the same principle, talking about charge injection interface engineering, also apply, because this is a similar type of electronic devices. So in that, okay, in order to really build a very nice device, you need to have relatively robust, because we focus on solution processing, right? So solution processing based on utilized solvent, your top solvent cannot, the solvent you use cannot dissolve the bottom layer, right, or erode your bottom layer. So you need to create very robust so-called whole transport layer. Instead of just utilize vapor deposition, you can do layer by layer. But then our work here is actually, because limited by the time, I only try to focus on some development of whole transport layer. So, and also some of the interface of the so-called conjugate surfactant at the cathode area allow us to inject hole and inject electron very efficiently. So when we find suitable complex and recombine in the middle range in here, they can dramatically enhance the device performance out of that, okay? So this is one slide to summarize some of the work. We can basically take any of the so-called whole transporting molecule and utilize different kind of functionality. So you spin this small molecule, then you heat it up, okay, in situ. You shine a light or heat it up. They form very nice cross-link network, okay? As a result, you have very robust mechanical property. So you can see that this is basically, you have some whole transporting molecule. When you spin that, it forms very smooth film and very electrochemically active, okay, material. So based on that, we demonstrate one of the very challenging tasks in LED is to make the quantum dot-based LED. Okay, and this is solution processable quantum dot LED. You know, you can based on your cross-link whole transport material. Now you take quantum dot and then you spin coat the 1 monolayer of quantum dot on top of this LED. Okay, depends on the concentration. You can manage to only have 1 monolayer. So this is about 5 nanometer. Then you evaporate on top of that your electron transporting layer. Okay, so you build your device on that. Okay, and the beauty of this is when you have a cross-linkable whole transport material, this can allow you to build a cascade your whole injection. Okay, toward very low lying band for your quantum dot. Okay, as a result, now electron coming from here, a hole coming to here, then you have very well confined exciton formation on your quantum dot. Then you have a very beautiful emission, narrow emission from that. Okay, so this is one very efficient LED we made. But recently, try to work on the electron transporting layer part. Okay, we have developed this so-called conjugate surfactant. Okay, so this surfactant, you know, we try to develop this material can be generally soluble in alcohol as a solvent, right? So this side chain serve a couple of different purposes. And one is the hydroxyl group will be chelating toward the metal electrode. You evaporate on top of that. And the nitrogen here will form positive surface dipole. Okay, as a result, you can adjust your work function of the top metal you use. Okay, so you know we try to demonstrate this concept on one type of a fluorescence material in here. You can see that we have 3 different kinds of cathode we use. Okay, and on top of this use as a cathode, one is based on use a very low work function metal like calcium, and another one is aluminum. And aluminum has a work function of 4.2 eV, much higher than calcium. Okay, so you have much higher energy barrier for electron injection. But then we have this conjugate surfactant. Okay, with aluminum. You can see that with only aluminum, and compared to that, okay, you have about 2 order difference in device performance. Okay, for your electron injection. Okay, and also you have much higher brightness out of that. So by utilizing both whole transform layer and also this conjugate surfactant, by taking 2 of the relatively efficient complex, blue emitting complex and orange emitting complex, you can adjust the ratio. Then you hit the sweet spot here. You can have very nice white light emission out of that. Okay, and this is 2007 already exceeds the incandescent light bulb. Recently, by further doping a little bit salt in that to improve the mobility of this conjugate surfactant, we have reached the power efficiency about 50 lumen per watt. This is one of the highest ever been reported for a polymer-based LED. Okay, so this is talking about when you take experimental device, then you try to scale it up and form very nice white light for solid-state lighting. And in one of the Boeing sponsored program, we actually are developing a solid-state lighting for aircraft cabin. Okay, so one day, okay, you know, I'm not promising you in the near future, but then one day you walk into 787, right? Okay, there's a dream airliner, and you find out all the fluorescent light tube disappear. Then you have just a polymer film, just a paste on top of that. That is due to top of this work. Okay. And with that said, we were talking about, you know, the potential economical and environmental benefit for solid-state lighting, right? So if we can, because currently 30% of electricity in the United States utilized for lighting, okay? And if you can really have a much more efficient solid-state lighting to as a lighting source, okay? Then you can potentially save about $125 billion. Okay, people did a calculation. And you eliminate about 250 million metric tons of carbon dioxide emission, okay, in the air. Okay, so this is not trivial. Okay, actually, dramatically, just by one application, you can significantly impact your environment. Okay, so with that said, you know, when we consider the energy. Okay, we need to consider this as a coherent solution. Okay, because not only you need to have very efficient energy generation source, you need to also have the very nice mechanism to store whatever the electricity or charge you generated. Okay, and the other part is how do you efficiently and smartly use your energy. Okay, so with that, you can significantly cut down the need for burning the fossil fuel and cut down the air pollution and also the global warming. Okay, and this dramatically will also, this is energy and environment actually goes hand by hand together. Okay, so if you can provide good solution to energy, then you actually can really impact your environment. Okay, with that, I would like to thank you for your attention, but also thank all my group members. They have done a wonderful job in different research areas. And this was taken actually in the wintertime of Seattle to prove to you, okay, Seattle doesn't rain all the time, okay. We have a clear sky, so the campus is wonderful. So thank you very much for your attention. Yeah.
Questions for Alex?
You have talked about many fascinating ideas. Is the solid-state light the one that's closest to commercialization?
Yeah, actually, we try to put together a startup company together, try to commercialize the solid-state lighting. Okay, and yes, I think Princeton, you also have UDC is heavily try to commercialize the small molecule-based solid-state lighting. Okay, so I would think the solid-state lighting based on OLED will be very close to commercialization. Okay, within the next couple of years.
What are the obstacles? Why is it not done yet?
So, well, when you're talking about that, usually you're talking about the solid-state lighting based on OLED or PLED is derived from the originally their purpose for flat panel display. Okay, flat panel display, if you look at that, is modulated by active matrix. Okay, so the pixel doesn't light all the time, right? So you can prolong the lifetime, and then the OLED people already demonstrate that your lifetime of your device can last for more than 100,000 hours. Okay, so but for solid-state lighting, the challenge is stronger. Okay, because if you light up the room, right, the light remains at a high intensity all time. Okay, right, at maybe say 100 candela. Okay, for example, that's typical. If you look at in a fluorescent tube, okay, 4 of those fluorescent tube as a set produce 5,000 candela. Okay, of light. Okay, then if you light up in the room, often you light up for hours, right? Maybe tens of hours. Okay, so that take a relatively strong hit on their lifetime of devices. So for solid-state lighting, I would say the device lifetime right now is around maybe less than 100,000 hours. It maybe say between 10,000 and 50,000 hours. Okay, so this is depends on application. Always talking about the cost. Okay, and also lifetime. Okay, how often do you really want to change your lighting fixtures? Okay, so if you can develop your material can be competitive with your current lighting system, I think that you can start to deploy that. Yeah.
So Alex, I'm going to pick up on cost. With the solar cells, you had talked about low cost, but the PCB and the C60 derivative, it's about $100 per 100 milligrams, right? So that's still pretty expensive. Any plans on replacing the acceptor?
So this is the thing, right? If you look at the roadmap we are doing, right? Okay, so if you look at the continuing in the effort of developing new materials, okay, and we have actually now focused on developing, also very nice N-type material, okay, potentially, can serve two purposes because C60 basically only transport the charges, right? Okay, don't really absorb light. Okay, so now you can say, how can I take the N-type material, not only I can also absorb light, but also can transport electrons. Okay, so I think that can be done. Okay, with our recent development to have a versatile, different kind of acceptor we develop. Okay, through the knowledge we have for nonlinear optical material development, I think that can be resolved. Yeah. Yes. Because, for example, gallium nitride is based on a blue LED. Okay, blue LED, the efficiency of the inorganic, and it's actually for blue color is actually the deficiency for organic material. Because organic material, one of the weakest point is the blue material. Okay, they have very high efficiency for red and green. Okay, because blue complex usually have much higher energy, as a result, much less stable. Okay, so if you look at why all those OLED haven't been commercialized, because you make an active matrix. Okay, after you run for a while, the blue will selectively fade away. Okay, because of it only lasts for maybe say 10,000 hours. But the efficiency of that, okay, I think for blue LED, okay, I think that lower than the gallium nitride LEDs. Okay, typically for blue LED, you can get about 20 to 25 candela per amp. Okay, but then I think the gallium nitride is significantly higher than that. Yeah.
Just wanted to pick up on both Jim's and Lynn's questions and ask about the lifetime for the photovoltaic devices. Even if you get the cost per watt down to say 50 cents or something, I mean, if you have to repaint Arizona every 3 years, it's not so cheap. In fact, so lifetime's an issue for those too, right? Where do we stand now?
So lifetime, okay, people did some accelerated testing, okay, for packaged solar cell, right? Okay, Kanaka did some of the measurement of that. They already proved that right now is you can go beyond 10,000 or 15,000 hours, because they just start to collect the data of that. Okay, so I think that with advancement of the encapsulation, okay, you can improve that. And also remember that the solar cell you are using not necessarily to just for your on top of your roof, right? You can have a lot of things for your portable electronics, right? Okay, so when you started talking about how long would you utilize your cell phone? Okay, how long would you utilize your laptop? How long would you utilize your Palm Pilot? You're talking about 2 years or 3 years time. Okay, so if I can have my device lifetime go beyond 15,000 or 20,000 hours, okay, so you already fulfill all those portable electronics use, okay, and then you said, okay, how can I continue to engineer that? But with people right now, because this flexible electronics, okay, is also one of the biggest market, talking about microelectronics right now, right? Okay, so people spend a lot of time trying to engineer the nanostructure, layer by layer, to position some of their polymer substrates, right, to prevent the moisture and the oxygen from diffuse through your material. So I think with those combined efforts, you can really address your application need. First, I think from shorter lifetime part. Then you're talking about, for maybe if I said, okay, now how about if I make it semi-transparent, okay, I can let me protect in between the two windows, seal that, okay, and then you provide very good encapsulation substrate for your devices instead of just put it outside, right? We can put it, between the two pieces of glasses, right? So as a result, you can dramatically also improve your lifetime, okay, your devices. Okay? So I think that we need to always have open, quite open mentality, because everybody will first thing talk about is lifetime of your organic, right? I've been hammered by that in my whole career. Okay, talking about people talking about develop device for telecom application. They said, okay, first thing you make a modulator, and then you put that undersea cable. Okay, you don't dig it out every year to fix it, right? So you need to have a lifetime of 40 years, okay, above, okay. So can that be achieved? I think so. You can achieve that because people prove that already, right? We can develop material to actually step by step to fulfill all the telecodia, the very stringent requirements, okay. If you can meet telecodia requirement, you can meet some of the organic electronics requirement, okay. So this, I think, the knowledge or the technique you learn from different kind of industry, you can actually integrate them together to really significantly improve your lifetime with devices. Yes? Okay. Okay, so which one are you talking about? This one? Oh, this one. This one? Okay, so this is a invert device structure, right? I take the most sensitive part of my device, actually embed it, okay? Utilize my glass as a protection layer to protect that. So then this is, but in order to do that, you need to be effectively collect electron through this, this direction, right? So my self-assembly monolayer on top of this either titanium oxide or zinc oxide, all those are very good electron transporter, okay, layer, okay, metal oxide for electron transporting. So electron transporting through that is no problem, can be collected by ITO. But now you have polymer blends. When you have a polymer blends, you have P-type material, you also have N-type material, right? So if you have both of those material touch the surface, okay, of that, right? So sometimes the charge selection is a problem. You have both charge can try to leak through your device. So if I have a C60 in here, right? C60 serve a function as a blocking layer, but also as an electron selecting layer because hole doesn't go through C60, okay? Electron can go through C60. As a result, you only select electron go through this cleanly. Okay, hole will be going up to the anode side to be collected. As a result, you can have a very efficient collection of your charges. Okay, to form the devices. So in here, right? This is a different thing I would like to prove to you is. On the positive side in here, anode, okay, I can collect hole from here, okay. But then from here, I try to collect electron from this side, right? Okay, the same direction is this same on top of that. Instead of C60 SAM, I now take the dipolar SAM, right? SAM with, for example, with a different dipole moment, okay. Through this dipole moment, I can adjust the work function of the top metal code on that. So instead of use low work function metal as a cathode, right, to collect electron, I can use high work function metal, okay, which originally have a relatively large energy barrier, okay, cannot really give you the maximized open circuit voltage, okay, right? You only have a very small VOC, okay. Now I can, depends on the dipole I use, I can get all the maximized VOC out of that, okay? So in that set of experiment, I'm trying to show you, okay, utilize SAM to really, optimize your open circuit voltage, but also you can get all the other benefit, get a very nice low series resistance and also very high shunt resistance means you have less current leakage leaks through those kind of layers. Yeah. Okay.